This series of videos about the Taylor and Maclaurin series is a little bit weird because it starts out with this big ol' if, but I'm going to phrase it as suppose. Suppose a function f of x has a power series representation centered at a. For our purposes, that means that a is at the center of the interval of convergence. And we'll say that f of x has the representation, the sum as n goes from 0 to infinity, of c sub n times x minus a to the n, where absolute value of x minus a is less than r, the radius of convergence. We're going to go through a process by which we're going to be able to determine the coefficients of each term c sub n. I'll start by expanding out the series. F of x is equal to, now folks, if you're taking notes, leave a little space in front of the f of x because I'm going to be writing something there in a little while. F of x is equal to c sub 0 plus c sub 1 times the quantity of x minus a plus c sub 2 times the quantity of x minus a squared plus c sub 3 times x minus a the quantity cubed plus c sub 4 times the quantity of x minus a to the fourth power plus dot dot dot. Ran out of room there, but that's okay. That's all I wanted for now. For reasons unbeknownst to us, we are going to compute derivatives because we can, and the derivatives of f, we're just going to use the power rule. F prime of x is equal to c sub 1 plus, and what just happened? C sub 0 was a constant. When I differentiated, it went to 0. C sub 1 was a coefficient of a linear factor of x. Well, it was x minus a. But when I differentiate that, the x drops out. I end up with the constant c plus 1. For the rest of the terms, the power rule will make it pretty easy to see what's going on. 2 times c2 x minus a plus 3 times c3 x minus a the quantity squared plus 4 times c4 x minus a the quantity cubed plus our dot dot dot. We're going to do that a few more times. The second derivative kills the constant c1. It differentiates to 0. 2c2 is the first term then. Using the power rule, we have 6c3 times the quantity of x minus a. Again, the power rule, plus 12c4 times x minus a the quantity squared. Continuing on, f triple prime of x, well now how far is this going to go? Just a couple more steps here, is going to be 6c3 plus 2 times 12, so 24 times c4 x minus a plus, now let's see if we can predict what the next term would be had we written it all down. The first term we did not write down in the expansion of f of x was c5 x minus a to the fifth power. Differentiating that would give us 5c5 x minus a to the fourth. Differentiating that, 5 times 4 times c5 x minus a the quantity cubed. So now we'd have 5 times 4 times 3 times c5 x minus a the quantity squared. That's 60 c5 times x minus a the quantity squared, but we still have plus dot dot dot. This will be the last one and we won't write very much of it. The fourth derivative of x is equal to 24c4 plus 120c5 times x minus a plus dot dot dot. That's enough. Now that we have all those, let's evaluate them at x equals a. Doing so will yield that f of a zeroes out every term that has an x minus a in it. So f of a is equal to c sub 0. For f prime of a, again, we're going to zero out all of the terms that have x minus a. So f prime of a is equal to c sub 1. F double prime of a is 2c2. F triple prime of a is equal to 6c3. And the fourth derivative at a is equal to 24c4. Now, when we started this process, folks, I told you that we were going to do something by which we could find c sub n's. We can take each of these and solve for the c sub n. But before we do that, what would happen for the nth derivative evaluated at a? Can we detect a pattern? The coefficients go 1, 1, 2, 6, 24, but think about where they came from, right? 24, 1 times 2 times 3 times 4. 6 was 1 times 2 times 3. 2 is 1 times 2. Folks, these are factorials. And you can see why. Remember how we developed C sub 5 had a coefficient of 60, right? We started out with 5 and then 4 times 3 times 2, and then eventually, the 2 gives us 120 times 1. So the nth derivative of f evaluated at a is going to be n factorial C sub n. Now, we could take each of these, f of a equals C sub 0, f prime of a equals C sub 1. We could solve for all the c's, or we can do so in general. That's what we're going to do now. What this tells me is that C sub n is equal to the nth derivative evaluated at a divided by n factorial. Now, does that account for the f of a equals C sub 0? It does, if we consider f of the function f as the 0th derivative. So let's go back up here. I told you we were going to leave a little bit of a space in front of f of x equals all the expansion that we wrote down, and it is that is the 0th derivative for f at x. That may show up from time to time. Folks, we have now found an expression for C sub n. It's based on derivatives of f. And so remember, this started out as f of x equals the sum as n goes from 0 to infinity of C sub n times x minus a to the n. So now we can bring this together and say that thus, if f has a power series expansion, that is, if it can be represented as a power series, then it is f of x is equal to the sum as n goes from 0 to infinity of the nth derivative of f evaluated at a divided by n factorial times x minus a to the n. I'll put that in a box because it's a really important result, which is called the Taylor series of f centered at a. At this point, I will remind you that n factorial is equal to 1 times 2 times 3 times dot 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 up to n, and that 0 factorial by definition is equal to 1. If it happens that the center of the power series is a equals 0, then it is called the Maclaurin series. So the only difference between a Taylor series and a Maclaurin series is that for the Maclaurin series, a is 0. For the Taylor series, a is anything but 0.